Hi everyone. I am Sham Parik. I'm a student of BSc Chemistry Honors first year. My roll number is 10 and today we are going to read the chapter S block elements. The elements of group 1 and 2 of the periodic table constitute the S block elements. These two groups are called S block as the last electron goes to S subshell. General electronic configuration is noble gas NS122. The elements of both groups are light and highly reactive. Electronic configuration. The electronic configuration of elements of both groups is given in the following table: lithium 3, sodium Na 11, and the electronic. First we will read about the group 1, which constitutes of lithium, sodium, potassium, rubidium, cesium, francium. That is Li, Na, K, Rb, Cs, and francium. Having the atomic number 3, 11, 19, 37, 55, 87 respectively, and with electronic configuration: helium 2s1, neon 3s1, argon 4s1, krypton 5s1, xenon 6s1, and radon 7s1. And for group 2 elements that are alkaline earth metals, we have the elements as beryllium, magnesium, calcium, strontium, barium, radium, with with symbols Be, Mg, Ca, Sr, Ba, Ra, with atomic number 4, 12, 20, 38, 56, 88, and having electronic configuration: helium 2s2, neon 3s2, argon 4s2, krypton 5s2, xenon 6s2, radon 7s2. The elements of group 1 are highly reactive and form strongly alkaline oxides and hydroxides. Therefore, these are called alkali metals. Francium is radioactive. The element of group 2 are called alkaline earth metals since these were alkaline and existed in earth. Radium is radioactive element. General characteristics of alkali metals. All the elements of group 1 are silvery, white, soft and light metals. These have simple chemistry than any of the other groups in periodic table. These have one electron in their valence shell and form univalent ionic and colorless compound. Some commonly used physical constants are given in below. Molar mass of group 1 elements in gram per mole: 696.94, 23, 39.1, 85.5 and 133. This sequence will be for lithium, sodium, potassium, rubidium and cesium. Density 20 degrees Celsius, 0.634, 0.972, 0.859, 1.53, 1.9. Molar volume 12.97, 23.68, 45.36, 55.80, 69.95. Melting point 180.0, 97.8, 64.0, 38.9, 28.7. Atomic radius 1.34, 1.54, 1.96, 2.11, 2.25. Ionic radius 0.68, 0.98, 1.33, 1.48, 1.67. Heat of atomization 159.0, 108.1, 90.2, 82.1, 78.2. And electronegativity 1.0, 0.9, 0.8, 0.8, 0.7. Density of alkali metals is quite low. Lithium, sodium, potassium are lighter than water, even though the elements have closer packing of metal atoms, but because of large size of alkali metals, they have low density. Density increases down the group top to bottom. Potassium is lighter than sodium. This is due to its large atomic size. Atomic and ionic radii. Atomic and ionic radii of alkali metals are largest in their periods. From top to bottom, the atomic and ionic radii increases in a group. The size increases because number of shells of electrons increase from one element to another in a group. As the number of shells electron increases, shielding effect also increases. Effective nuclear charge decreases, the outer shell expands further. Ionization energy. Alkali metals have lowest ionization energy in their respective periods. In a group, the ionization energy is decreased from top to bottom. This is because the atoms have large size and there is one electron held loosely by the nucleus in the outermost shell. By losing one electron, they acquire stable noble gas configuration. The second ionization energy, i.e. 2 of alkali metals, is very high. This is because after losing first electron, atom changes into cations which have high effective nuclear charge. Cations of alkali metals have noble gas configuration which is very stable. Melting and boiling points. All the alkali metals are soft and low and have low melting point and boiling point. This is because they have only valence electron per metal atom. Therefore, the energy binding the atoms in the crystal lattice of the metal is comparatively low. The melting point of lithium is 180 degrees Celsius, while cesium metal has 28.7 degrees Celsius. Thus, melting and boiling point decreases down the group. Electropositive or metallic character. Tendency to lose electron and acquire positive charge is called electropositive character or metallic character. All alkali metals are strongly electropositive. Electropositive character is related to ionization energy. Since ionization energy of alkali metals are low, these have high electropositive character. As ionization energy decreases down a group, electropositive or metallic character increases from top to bottom in a group. Oxidation state. Alkali metals have one electron in the outermost shell, and alkali metal loses their loosely bound electron and show +1 oxidation state in their compounds. After losing one electron, Monovalent ions M positive with noble gas configuration are formed. The ionization energy too are very high due to stable configuration after losing first electron. Therefore, alkali metals show +1 oxidation in all their compounds. Photoelectric effect. The phenomena of ejection of electrons from the surface of metal when light of suitable frequency strikes on it is called photoelectric effect. Alkali metals show photoelectric effect as they have low ionization energy. Cesium has lowest ionization energy, therefore it shows photoelectric effect. This metal is used largely in photoelectric cells. Characteristic flame colorization. The alkali metals impart characteristic colors to the Bunsen flame. The alkali metals have larger size and in their respective periods, hence they possess low ionization energy. When the alkali metal or their salts are heated in the Bunsen flame, the energy provided by the flame is sufficient to excite the electrons to higher energy levels. The excited state are unstable and the electrons tend to come back to the ground state. When the electrons return to the ground state, the excess of energy is released in the form of radiations which lies in the visible region of the spectrum. The alkali metals in their flame color are shown below. For lithium it is crimson red, for sodium it is golden yellow, for potassium it is violet, for rubidium it is violet, and for cesium it is violet. Lattice energy. It is defined as the amount of energy released when 1 mole of ionic solid is broken into its constituent ions mxs. Lattice energy M positive plus X negative. The salts of alkali metals are ionic in nature, consist of cations and anions held together by electrostatic force of attraction. Therefore, lattice energy of alkali metal salt is very high. Lattice energy is a measure of force of attraction between the ions. It depends upon the size and charge of the ions. Since charge on the cations of alkali metal salt is same, the lattice energy of salts for same anion decreases with increase in the size of cation. This is due to decrease in the force of attraction between the ions. Basic character. Hydroxides of alkali metals are most basic in nature. The basic character increases down the group region. Alkali metals have larger size in their respective period, therefore they have least ionization energy. The metal hydroxide OH is ionized due to large size of alkali metals to M positive and OH negative ion. As the size increases down the group, the ionization energy decreases and basic character increases down the group. NaOH is stronger base than LiOH and KOH is stronger as compared to NaOH. Chemical properties. The alkali metals are highly reactive due to large size, low ionization energy, and low heat of atomization. The important chemical properties and the trends are as follow. Action with air. All alkali metals tarnish rapidly on exposure to air due to the formation of oxides at the surface. The oxides may further react with CO2 and moisture to form layers of carbonate at the surface. These are therefore stored under kerosene to protect them from air and moisture. The alkali metals burn vigorously in air, forming three types of oxides: normal oxide with O2 minus ion, peroxide having O2 2 minus ion, and peroxide containing O2 minus ion. The product depends upon the nature of metals. Lithium forms only oxide Li2O, sodium forms peroxide and Na2O2, potassium, rubidium, cesium forms superoxides Ko2, RbO2, CsO2. This can be explained on the basis of size of cation and anion. Smaller cation can stabilize smaller anion, larger cation can stabilize larger anion. Now Li positive ion has smaller size and therefore it stabilizes small anion O2 minus because of strong positive field around Li positive. It prevents the spreading of negative field towards other oxygen atom. Therefore, it cannot attach another oxygen atom and higher oxides are not formed. Na positive ion is large and can stabilize large anions. The K positive, Rb positive, Cs positive are still larger cations and have weak positive fields which allow the formation of superoxide ion O2 minus ion. Action with water. Alkali metals react rapidly and readily with water, forming hydroxides and liberating H2 gas. 2Na plus 2H2O gives us 2NaOH plus H2. Lithium reacts slowly but reactivity increases from lithium to cesium. For potassium, rubidium, cesium, the reaction is so fast that evolved H2 catches fire, so these are kept under kerosene. Action with hydrogen. Alkali metals react with hydrogen to form hydrides. 2M plus H2 gives us 2M positive H positive. Ionic character hydrates increases down the group. Reactivity of hydrates increases down the group. Stability of hydrates decreases down the group. All hydrates are strong reducing agents. Solution in liquid ammonia. Alkali metals dissolve in liquid ammonia to give blue solution. The ammonia molecules solvate the cation as well as the electron. The value of X and Y depends upon the extent of solvation of cation and electron. The ammoniated electron is responsible for blue color of the solution. The solutions are paramagnetic due to presence of free electron. The solutions are strong reducing agents. The solutions can reduce aerial oxygen into superoxide and peroxide. On standing for long duration, the solution liberates H2, reducing nature and oxidation potential. All the alkali metals are strong reducing agents. This is because of their low ionization energies. Their reducing nature is indicated by the large negative values of the reduction potential. Standard reduction potential of alkali metals. For lithium it is 3.04 volts, for sodium it is 2.71, for potassium it is 2.92, for rubidium it is 2.99, and for cesium it is 3.02. Lithium emerges as the strongest reducing agent, though its ionization energy is maximum among alkali metals. This can be explained if we recall that ionization energy is a property of isolated atoms in gaseous state. Oxidation is the property when metal goes into solution. This involves three steps. Metal solid gives us metal gaseous. In sublimation energy, metal gas when ionized gives metal positive plus electron. In metal positive plus H2O gives us hydration energy and gives it a metal positive in aqueous form. This oxidation potential is a tendency for overall change which depends upon the net effective of all three steps. Since Li positive has the smallest size, so it is hydrated to maximum extent. The large hydration energy of Li positive ion compensates the higher energy needed to remove electron in the second step. Thus, lithium is the strongest reducing agent because of its greater hydration energy. Question: how does lithium differ from other members of the family? Due to small size and high polarizing power, lithium differs from other alkali metals in the following perspectives. Lithium is much harder than other alkali metals. Its melting point and boiling point are also higher. It is least reactive of all alkali metals. Lithium is the only alkali metal which reacts with nitrogen to give Li3N. Lithium burns in oxygen and forms monoxide Li2O, while other members form peroxide and superoxide. Lithium reacts with bromine slowly, while other alkali metals react vigorously. Diagonal relationship. Though lithium differs from other metal of its own group, it resembles with magnesium Mg, the second element of group 2. This is called diagonal relationship, in which first member of the group shows similarity with the second element in the next group on the right in the periodic table. Lithium forms only oxide Li2O, sodium forms peroxide Na2O, potassium, rubidium, cesium forms superoxide Ko2, RbO2. Causes of diagonal relationship. The cause of diagonal relationship are similar electropositive nature. On moving from left to right, the ionization energy increases, thus electropositive character decreases in the period, but on moving down the group, the ionization energy decreases, electropositive character increases. Thus, when we move diagonally, the two tendencies cancel each other. As a result, lithium and magnesium have almost same electropositive character. Similar polarizing power from left to right in a period, the ionic charge increases and size decreases. This increases the polarizing power, but from top to bottom in a group, the charges remain same and the size of the ion increases, the polarizing power decreases. Thus, when we move diagonally, these two effects partially balance each other and the polarizing power of lithium and magnesium remain almost same. Diagonal relationship between lithium and magnesium. Lithium and magnesium, in many aspects, the common features of this element are as the atomic radius of lithium is 1.34 and that of magnesium is 1.36 angstrom, which are not very different from each other. The ionic radius of lithium is 0.68 angstrom, is similar to ionic radius of Mg2 positive, which is 0.65 angstrom. Polarizing power of the two is about same. Both of them form monoxide. Li forms Li2O and Mg forms MgO. Lithium and magnesium both decompose water slowly, liberating H2. Both of them form nitride on heating with nitrogen. LiCl and MgCl2 is deliquescent, absorbs moisture on exposure to air. LiOH, like MgOH, is a weak base. Now we will discuss about the group 2. General characteristics of group 2 elements. The various physical constants of alkali metals are given as follows: atomic number, atomic mass, atomic radius, ionic radius, ionization energy, oxidation state, melting point, boiling point, and now we will discuss about the physical properties. Atomic and ionic radii. Size of group 2 elements is large, though smaller than the element of group 1 due to higher nuclear charge. The atomic and ionic size increases down the group. Melting and boiling point. The melting point and boiling point of group 2 elements are low but higher than alkali metals. This is due to smaller size of atoms which fit tightly into crystal lattice. Ionization energy. Due to large size, these have low ionization energy. Ionization energy decreases down the group as size increases. Compared to alkali metals, ionization energy of group 2 elements is still high due to comparatively smaller size. Tendency to form ions in +2 oxidation state. Alkaline earth metals form bivalent +2 ions. First ionization energy of alkaline earth metal is higher than alkali metals, but second ionization energy of alkaline earth metal is lower than that of alkali metals. From ionization energy, it appears that alkaline earth metal would form H ions rather +2 ions, but they form +2 ions. Example: Mg2 positive, Ca2 positive. This is due to the following reasons. +2 ions have stable noble gas configuration. In solution state, +2 ions are small and hence undergo extensive hydration. This large amount of hydration energy is more than required to compensate for the second ionization energy. Moreover, +2 ions show high lattice energy in solid state. The high lattice energy compensates for the ionization energy too and provides greater stability. Basic nature of hydroxide. The alkaline earth metals take with water to form hydroxide. The reaction is slow as compared to alkali metals. Hydroxides are basic in nature, and basic characteristics of hydroxide increases down the group because on moving down the group, ionization energy of alkaline earth metal decreases. The metal hydroxide bond becomes weak, and oxygen and OH minus ion is easily released. So basic character of hydroxides increases down the group. Flame colorization. Group 2 elements also give color to the flame due to low ionization energy. On hitting the electron of the valence shell, get excited to higher energy level. The excited states are unstable and the electrons get back to their ground state by emitting heat energy in the form of radiation which falls in the visible region. This gives characteristic color to the flame. Why beryllium and magnesium do not give color to flame? Size of beryllium and magnesium is small in their group, therefore they have high ionization energy. The heat provided by flame is not enough to excite the electrons, hence no color is imparted to the flame. Nature of metal bonding. In alkaline earth metals, 2 electrons per atom take part in metallic bonding. Moreover, the atoms are small and hence closely packed as compared to alkali metals. That's why alkaline earth metals are harder, denser, high melting point and boiling points, and higher heat of atomization. The metallic bond strength decreases down the group as size of atom increases. Diagonal relationship of beryllium with aluminium. Beryllium shows diagonal relationship between aluminium because both have similar charge to size ratio, similar electronegativity, similar enthalpy of vaporization, similar polarizing power. The similarity in beryllium properties are shown. Both from covalent compound, both become passive on treatment with concentrated HNO3. Both are weakly electropositive in nature. BCl2 and Al2Cl6 form bridge polymeric structure. Carbides of the boron and aluminum liberate methane with hydrogen. Salient features of hydrides of S block elements. Elements of S block group 1 and group 2 are electropositive, hence they all form ionic hydrides with hydrogen. Hydrides are ionic, white crystalline solid. The ionic nature increases down the group. The hydrides are not very stable and hence react with water releasing H2. Hydrides are strong reducing agents. They reduce organic acids to alcohols. These hydrides can be used to prepare complexes. Structure of hydrides and S block elements. Hydrides of group 1 elements LiH, NaH, etc. have NaCl type structure. BH2 and MgH2 are polymeric solids. These are electron deficient compounds. When one beryllium atom is bonded to 4 hydrogen atoms, banana bond is special feature of these compounds. When 3 atoms are bonded by 2 electrons, these bonds are called 2 center 2 electron bond. Anomalous behavior of beryllium. Beryllium differs from other members of same family. That is due to the following reasons. Beryllium has small atomic and ionic size. It has high ionization energy. It has high electronegativity. It has high charge density and absence of d orbital. Beryllium differs from other members of its group in following ways. Beryllium is harder and denser than remaining member as beryllium has small size and fits compactly in crystal lattice. It has very high melting point. The ionization energy of beryllium is very high due to smallest size. Beryllium forms covalent compound while other members form uric compound. Beryllium oxide is amphoteric while oxides of other members are basic in nature. Complexion tendencies of S block elements. Tendency to form coordinate compound lacks in both alkali and alkaline earth metal. This is because of the large size, low charge and absence of vacant orbital of low energy in ground or excited state. However, alkali metals form complexes with chelating groups like salicylate, halide. Such ligands are strong complexing agent because these are multidentate and form ring compound with metal ions. For example, Na positive forms salicylidehyde complex. Na positive ions set in a coordination number of 4. However, potassium, rubidium, cesium can form 6 coordinated with salicylidehyde as salicylidehyde. Similarly, group 2 elements have small size and have higher charge. Thus, this should be better at complexing as compared to group 1 elements. BeF to coordinate with 2 fluorine atoms to form tetrahedral complex BeF4. The most important complex on this planet is chlorophyll formed by magnesium. All life depends ultimately on chlorophyll and photosynthesis. Mg sits at the center of flat heterocyclic ring organic system called porphyrin. Here, 4 nitrogen atoms are bonded to magnesium at the ethylene diamine tetraacetic acid is a hexadental ligand which has 4 oxygen and 2 nitrogen donor sites at the complexes with Ca2 positive and Mg2 positive. This process is used in determination of hardness of water. Complexes of alkali metal ions by cyclic polyethers. Crown ethers are macrocyclic polyethers synthesized by C.J. Pedersen for the first time. These are called crown ethers because the atoms form crown-shaped rings. Crown ethers bind the cation strongly and selectively. For example, KMnO4 dissolves in benzene only in presence of 8 crown 6. From various experiments, it has been found that a close fit is possible when the cavity size of polyether matches with the size of cation. Cryptates. Cryptates are polycyclic ligands that contain other donor atoms like nitrogen, sulfur or phosphorus etc. In addition to oxygen. These are even more selective than crown ethers. The structure of one such cryptate 222 crypt is like that. Sodium forms the compound with Na222 crypt, Na positive in ethylamine solution. It is golden yellow diamagnetic solid stable up to minus 10 degrees Celsius. The interesting feature of this compound is that it contains sodide ion Na negative. The cryptate ligand shields the Na positive ion and prevents it from uniting with Na negative ion. Difference between crown ethers and cryptates. They differ from each other in the following ways. Crown ethers are monocyclic polyethers while cryptates are polycyclic. Crown ethers have only oxygen as donor atom while cryptates have nitrogen, sulfur and potassium, phosphorus in addition to oxygen as donor atom. Function of S block elements in biosystem. Role of Na positive and K positive ions. A required level of Na positive and K positive level is maintained in extracellular intercellular fluids through sodium pump. This results in the development of electrical potential across the cell membrane. It is responsible for the functioning of the nerve and the muscle rings. Role of Mg2 positive and Ca2 positive ions. Mg2 positive ions are present in chlorophyll, which is responsible for life on earth. Mg2 positive ions activate phosphate transfer enzyme, which help in releasing energy in animal bodies. Mg2 positive ions are also required for carbohydrate metabolism. Ca2 positive and Mg2 positive ions are responsible for transmission of nerve impulses and contraction of muscles. Ca2 positive ions help in the formation of teeth and bones. Ca2 positive ions help in blood clotting. Ca2 positive ions maintain regular beating of heart. So this was all about our S block elements. Here we have covered both group 1 as well as group 2. Group 1, that is alkali metals, and group 2, that is alkaline earth metals. So that was all for today's video. Thank you all for watching and subscribe my channel for more such videos.